Hello, welcome to the 10.2 lesson, Molecular Bonds. We're going to go over hybridization, which is review from the 10.1 notes, as well as the sigma and pi bonding and what that looks like on an AP question, or like just a couple examples in general. So to review back hybridization, we had the blending of orbitals, right? So hybridization means you're creating a hybrid of your s and your p orbitals, right? All of your s orbitals had that spherical shape, and your p orbitals was those three dumbbell shapes, right? So if I go ahead and I add the other dumbbell shapes, there's one on the y-axis, there's one on the x-axis, and then there's one on the z-axis, right? So it's p, there's three different p shapes. If we were to draw out, like say 2s, that's just one orbital, right? One orbital shape, whereas 2p had three different orbital shapes. Well, at some point, they hybridize. And so you create your s and your p orbitals, and they come together, and they create your sp, your sp2, your sp3 orbitals. And so they kind of create like an intermediate form of all the shapes together. And so if we go ahead and look at the next couple slides, it explains CH4. So CH4 is methane, and we have to look at how did we come up with, or how did scientists discover that hybridization actually existed, what proof exists for that. And they've studied the electron configurations, right? We've done 1s2, 2s2, 2p6, so on and so forth. And there's a certain way that elements and those electrons position themselves in such a way that they can share with another atom, right, in order to fulfill that octet rule. And CH4 is a really good example to look at. So the ground state of carbon is 1s2, 2s2, and then 2p2. But there's a problem with this. If we look at carbon, carbon should have 4 valence electrons to it, right? So if I were to draw carbon and the valence electrons around carbon, it should be 1, 2, 3, 4. That means that it has 4 possibilities to bond, right? So it can bond with 1, 2, 3, 4 things, and it can be 4 single bonds, it can be 2 double bonds, a triple and a single, right? But it has a possibility to make 4 different connections because it's in group 4. But if we look at this valence electrons right here, the 2s2, 2p2, this only says that there's 1, 2 unpaired electrons. So that means there's only 2 bonds. So how do we get those 4 bonds, right? We need to have 4 unpaired electrons, and right now with our ground state electron configuration, there's just 2. And so that's kind of where hybridization came about. And so if we look at the next slide, there we go. And that's exactly what I just said. We're going to go ahead and take that 1 electron from the 2s and move it over to that empty orbital in the 2p, right? And so we take this electron from the 2s and then move it over to the 2p. So now we have 1, 2, 3, 4 unpaired electrons. If you have an unpaired electron, that means that there's a potential or a possibility to make that many connections, right? Every unpaired electron wants to make a connection if possible. And so we have 1, 2, 3, 4 unpaired electrons now because it hybridized. But exit this annotation. If we look at this next side, right? If we look at CH4, so the carbon's in the middle, it's in the intersection between those 2 lines. There's 1, 2, 3, 4 things that can be attached to it. When there's 4 things that can be attached to it, it's going to create an sp3 hybridization. And so what we mean by that is the 2s and the 2b kind of fuse together, and such a bond would have slightly less energy than the other bonds in the methane molecule because they become a lower energy level than normal. Right, so if I go over through this slide, it says this bond would be slightly different in character than the 3 bonds in methane. The difference would be measurable to a chemist by determining the bond length and the bond energy. But when we look at methane, you can't determine any difference. Right? Measurements show that all 4 bonds in methane are exactly equal. Thus, we need a new explanation for how the bonding works in methane, and that is hybridization. So it's where you combine 2 or more orbitals of nearly equal energy in the same atom of orbitals of equal energy, right? So we have our 2s and our 2p, and normally s is lower in energy than our p, and p is higher in energy. That's our Aufbau's principle, right? But when we hybridize, they notice that if you have like sp3, right? So we have sp1, 2, 3, s1, 2, 3, that's 2sp3. they're all going to be about the same energy level. And so that means that they kind of shift, right? So they're going to be an intermediate energy level in between, and they hybridize to make that new energy level, that new shape, that new orbital. I believe that's the next slide right there. Yep. And so these new orbitals have slightly more energy than the 2s, but a less energy than the 2b. So again, they're an intermediate energy level. If we look at sp3 hybridization, that's usually going to be 4 connections or 4 different attachments to the central atom. And it's going to have 1, 2, 3, 4 sp3, right? That's all the sp3 shapes right there. So we have the s and then all 3 of the p's combining together to make 4 new shapes, 4 new attachments. And usually these bond angles are around 109 or so degrees. The sp, did I skip? Nope. sp orbitals, the hybrid orbitals, we just take one of these s and one of these p's, and it creates hybrid orbitals here, right? So sp. And then the other 2 p's are just left alone, right? So we take the s, the p, they create SPs, and then these 2 guys right here, these guys get left alone. And so they don't actually have any energy change, they don't have any shape change or anything like that. Oh no, my battery is running low. Let me go ahead and plug in my laptop. All right. The next slide is sp2 hybridization. And so again, we take one of our s's, that one s shape, and then 2 of our p shapes now. And so that's going to create sp2, sp2, sp2. And then it leaves that 3rd sp by itself, right? There's one that remains unchanged. As far as the d orbitals, right, we have that 3d row and then 4d. We even have f. There's not a lot of evidence right now as including that those D and those Fs actually hybridize in the same way. For the AP test, you don't need to know it. They only do S, SP, SP2, and SP3 hybridization in the current course. So that's just an exclusion warning. So I'm going to skip those D ones. As far as hybridization and molecular geometry, whenever you have an SP, that's usually going to be single bond, perhaps double bonds, 2 attachments, right? You have one on the left, one on the right, for example. Our steric number for that, 2 attachments, is always going to be x2, right? So our steric number, remember, your x is how many things are bonding to it, how many bonding groups you have, that's your x. So it's your bonding groups, how many things are attached to it. And your E is your non-bonding electron pairs, so your lone pairs. And so 2 attachments is SP, right? 3 attachments, whether it's 3 bonding groups or maybe 2 bonding groups and 1 lone pair, that's still 3 attachments. Those are always going to be SP2. If you have 4 attachments, whether it's 4 actual bonding groups, 3 bonding groups, 1 lone pair, 2 bonding groups, 2 lone pairs, that's going to be your SP3 hybridization, right? And the general shapes, the general overall structures is linear, trinoplanar, tetrahedral. Now remember, for the VSEPR theory though, that if you have lone pairs, it's going to push them down. And so on your first lesson notes, that kind of goes through it. If you have an SP hybridization, that's 2 things attached to it, right? So that means there's just 1, 2 things attached. Whether it's a lone pair or no lone pair, it's going to be linear, flat line, 180 degrees, right? Trignoplanar, if there's 3 things attached to it, it's going to have a 120 degree bond angle, and it's going to create like this triangle shape, and it's up in the same plane, so it's a trignoplanar shape. But if there's a lone pair with 2 attachments, right, that lone pair right there is actually going to bend down those 2 attachments. So if I go ahead and clear those random 2 lines, this lone pair right here, because of that lone pair, it's going to kind of bend down these 2 guys, right? So an example could be water, or not water, ozone, right? Because ozone has 1 lone pair around it. And so it's going to take the left oxygen, push it down a little, the right oxygen, push it down a little. It's still sp2 hybridized, but it's going to be bent instead of trignoplanar. So just make sure you know how to name your shapes. Same with tetrahedral, right? sp3 hybridization, there's 4 things attached to it. If it's 4 bonding groups, it's tetrahedral. If it's 3 bonding groups with 1 lone pair, it's trigonal planar pyramidal. And then if it's 2 and 2, it's bent, right? And for the AP test, if you say any of these bond angles, they'll usually be a range, right? They don't expect you to memorize exactly 109.5 or exactly 104.5. If you say it within that range, right, 104 to 109 for sp3 hybridization, they'll accept that as a valid answer. All right, if we look at sigma and pi bonds now, sigma bonds exist in the region directly above, between 2 bonded atoms, and pi bonds exist above and below that. And so what I mean by that is if I have carbon attached to carbon, the region in between is your sigma bond. The region above and below is your pi bond. So if we have, let me clear these drawings. Right, if we have C2H6, it's just one single bond. If we have one single bond, this is going to be a, that should say sigma bond, but it's just going to be a sigma. Right, that should be sigma. And it's because of the region in between, right? Whereas if we look at a double bond, there's going to be a sigma bond in between, and then that one pi bond, that above and below, right? So this is C2H4. And if we look at ethane, C2H2, that's a triple bond, and it's going to be that region in between, still that sigma bond, as well as above, but then also to the side, right? So there's that one pi bond above and below, and then the other pi bond is to the side, to the other side. And that's just where the electrons like to kind of, it's the delocalized electron model. So Vesper theory, valence bond theory, all of that, it's been dealing with the localized electron model, that electrons like to stay to a local spot, right? You're a local to your city. Electrons usually, that's the previous model, but it doesn't explain a lot of the observations that we see for shapes and how chemicals react with certain compounds. And so to kind of expand on that, they created the delocalized electron model. And the delocalized electron model, again, like pi bonds, is just saying that the electrons can still be shared. They're just orbiting or moving around within a delocalized area. So it's not between 2 atoms necessarily, but it's going to be around, right? So if you have benzene, which is this molecule right here, the double bonds can be, you know, on the right, the bottom, the left, or they can be on the left, the side, and then the bottom like that. And it's that ring, the delocalized pi bonds, that makes that possible, right? So that's how you end up with resonant structures, where you can shift your double bond, you can shift your single bond depending on how many areas that it can attach to. And so if we look at our notes, a couple of the examples. Right, so C2H4, if we look at that one, we can do that one really quick. Right, so we have C2H4. We're going to go ahead and draw the 2 carbons in the middle, and then the 4 hydrogens on the outside. And always try to keep it symmetrical when you're drawing, right? If there's 4 hydrogens, put 2 on, and then 2 on the other side, 2 on one side, 2 on the other side. And I know that carbon needs to have 4 bonds to fulfill the octet rule. So 1, 2, 3, 4, 1, 2, 3, 4. Hydrogen is just a duet because of that 1s1, so it can only have 1 attachment. So it's just 2 electrons or 1 bond for each of the hydrogens. And if I look and I want to figure out how many sigma bonds, how many pi bonds are there, easiest, simplest way to do it is if it's a single bond, it's a sigma, right? So it's a sigma, 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 sigma. If it's a double bond, it's a sigma and a pi, right? So if I have to count 1, 2, 3, 4, 5 sigmas and 1 pi bond, right? And if we draw a representation of how that kind of comes together, how that overlaps, we have the carbon hybridizing, right? So this is spp, so that's sp2, right? And so that's my trigonal planar shape. And so I have an sp2 orbital, an sp2 orbital, and an sp2 orbital, right? So that's my 1, 2, 3. This guy right here, the hydrogen is just S, right? It's just S, it's just S. So it's gonna come together with an S shape, another S shape right there. Well, this carbon on the right-hand side is the same idea. So we have that sp2, we have, let's see if I can draw it, sp2, and we have that sp2, right? Because this is also sp and p, so sp2 as well. And then these hydrogens again are just S because there's just one attachment each. And so S and S. Well, that leaves that P, right? That third P is still missing. And so sp2, but there's that third P, right? That third P is just normal. Didn't change its shape, so it's going to be above and below. And that's what creates that pi bond right there, right? So the sigma bond is this connection between the sp2 on both of the carbons. But that pi bond comes from that P that was not hybridized, and so it's connecting the electrons above and below the two carbon atoms. Right? If I go ahead and look at C2H2, it's going to be the same idea. This time it's a triple bond. Right? So I have a single bond, which is sigma, another single bond, which is sigma, and then my triple bond is a sigma plus 2 pi bonds. Right? And so if I look at my hybridization to try to explain this now, I'm going to go ahead and look at carbon. This left carbon has sp, so it's just sp. Same with this right carbon. And then the hydrogen is S and S, right? So you're counting the connections to it, right? You have 1, 2 connections, so it's sp. 1, 2 connections, sp. 1 connection is S, 1 connection is S. So if I look at my sp, it's going to be, let's see if I can draw this properly. Right, you kind of have like a disformed sp shape, and then one connects to the S, the other one connects to the S, but that leaves 2 P's, right? It leaves this time 2 P's. And so we have a missing P on both of the carbon that did not hybridize, as well as a third missing P that did not hybridize. And so one of those P shapes is going to be up and down, right, on the y-axis. So it's going to connect above and below. So that's your first pi bond. But then the second pi bond, if I can draw it, is going to be kind of like sticking out on your z-axis. And so it's going to connect side to side. Right, so when you're drawing it or explaining it, I think the easiest way to do it is probably to draw it just really neatly, as neat as possible, but also explaining it, right? Why hybridization leads to your sigma and pi bonds, why that leads to your shapes, why that leads to your Vesper theory, your localized electron model versus your delocalized electron model versus your valence bond theory, right? I'm gonna go ahead and probably stop the video at this point so it's not too long. If you want to go over C and D on the examples, please let me know. Same thing with avobenzene. Try to do it yourself. We'll go over it if you have any questions on it. And then this last part, spectroscopy with electromagnetic radiation. They like to ask questions about this. So I would definitely take time, look at your electromagnetic radiation, radio waves to X-rays, what wavelengths they fall under. And then how that actually moves your bond, and then the applications for those. So I have seen a couple multiple choice questions, as well as I think maybe one free response question where they asked about that. And so it's more a matter of memorization and understanding how it applies to your Lewis dot structures, your Vesper shapes, your hybridization and sigma and pi bonds. Once you have it memorized and you can apply it, then it's not too bad at all. And then down below is just some graphs, some examples, some explanations of the different spectroscopies. So if you have questions, write them down and ask me at some point.